So expected value, I want to start with just the notion of an average if you have a collection of numbers. So suppose that a group of students has the following quiz scores: 3, 5, 8, 8, 8, 10, and 10. In this instance, notice that means there are 7 students. And if I wanted to find the average quiz score among these 7, I could add all 7 quiz scores and divide by the total number, 7. So in comparison to what we talked about before, we can notice that each student is equally weighted. But if I were to look at this average, the score values are not equally weighted, right? You can see we're more likely to list an 8 than say a 3 when I look at this. And so if I wanted to find the average and focus on the score rather than the student, we can think of that as a weighted average. So another way to compute exactly the same thing we did above, but to kind of group it in a different way, is I can say that 3 is weighted 1/7, 5 1/7, 8 3/7, and 10 2/7, and I get the same answer there. So this notion of a weighted average is that we think of the values that occurred and how likely those values were. So that leads to the idea of what we're going to define here that's a little bit more broad. And the idea is that we're going to have a random variable, x, and the values that this random variable can take on, so think about the range of x, includes x1, x2 through xn. Then I'm going to define the expected value of x as the sum from k equals 1 to n of x sub k times the probability that x is equal to x, this should be x sub k. And just as a reminder, this little p, that's the mass density function of x. And we saw that that's defined to be exactly the same as the probability that x takes on the input. So just again, more generally, notice that this sum has terms equal to the values that x can take on, weighted by the probability that those values occur. To see this in practice, let's look at an example. So suppose you flip a fair coin 3 times, and I'm going to let x count the number of heads. Find the expected value of x. So when I find the expected value of x, I need to know the mass density function. So even though that's not explicitly stated, we're really going to need that in order to compute this expected value. Taking it back even further, just for clarity, if I want to think about the sample space, again associating h to heads and t to tails, we could list out the possible outcomes of this experiment. And there will be 8 of these. And then remember that that means this is the domain of the random variable x, and we want to think about what numbers x associates to these outcomes. This would be mapped to 3. These 3 outcomes would all be mapped to 2. These 3 outcomes would all be mapped to 1, and this one would be 0. So again, where I'm getting those numbers is within each outcome, I'm counting the number of heads. So when I think about the mass density function, remember the range of the random variable is the domain of the mass density function. And so I need to find p of 0, I need to find p of 1, p of 2, and p of 3. By writing these down, I'm finding the mass density function. And again, these represent the probability that x takes on those values. So in the first case, probability that x is 0, that can only happen in one way out of the 8. The probability that x is 1, notice that there are 3 different ways x could end up being 1. And there are 3 different ways that x could end up being 2, and only one way that x could be 1. So I want to pause here for a moment and point out a common mistake is I will see people forgetting the 3 in the middle cases there. You can view this as each outcome has a probability 1/8 of occurring. And so in thinking about counting the number of ways that you can end up with x equaling 1, that's the multiplier of that probability of 1/8. And likewise here. So those 3 represent the fact that there are 3 different scenarios where I can see a sequence of 3 coin tosses where only one of them is heads. And that depends on whether that one heads occurs on the first toss, the second, or the third. For these extreme cases, you can see the multiplier is just going to be 1. The only way I can get 0 heads is tails, tails, tails. I know what has to happen on all 3 of the tosses. And likewise, the only way I can get heads, heads, heads to get 3 heads is just that one way. I, again, have complete information of what happened on each and every toss. As a good reminder, you know that the probabilities have to add to 1, and if I'd forgotten my 3 multipliers, I would have seen that that's not the case. Now, once I have the mass density function, then it should be very simple to compute the expected value. The expected value says we need to take all of the values that x can take on and multiply by the probability that it takes on those values. So in this case, yes, I could write out the sum in sigma notation. The values are k, and we're multiplying by the probability that x is equal to k. So to be clear, in this instance, these are like the x sub k's because the values x takes on are 0, 1, 2, and 3. So I can actually just use k to represent those in the sigma notation. However, I'll also point out, in a problem like this, where you need to add 4 things together, you don't need to write the sigma notation. That's going to be useful when we start to think about larger sums, even having infinitely many terms. So it's completely fine if you just jump right into the formula and writing out the terms. So we're going to take 0 times p of 0 plus 1 times p of 1 plus 2 times p of 2 plus 3 times p of 3. One thing that's worth noting is whenever you're finding an expected value and 0 is one of the possible values, we can always disregard that from the sum because you're taking the probability that x is 0 and multiplying it by 0. So it's never going to end up contributing anything. So now I take 1 times p of 1. P of 1 was 3/8 plus 2 times p of 2. P of 2 was 3/8. And plus 3 times p of 3, which was 1/8. So I see here that I can pull out a 1/8, and I have 3 plus 6 plus 3. We get 12/8 or 3/2. That's going to be our expected value. And then I also want to point out here, notice that the values x can take on are 0, 1, 2, and 3. Our expected value, 3/2, is not actually a possible number for it to take on. So in order to think about the significance of this, it's better to kind of think of expected value as a long-term average. If I were to do this experiment many, many times, so flip 3 coins, count the number of heads, flip 3 coins, count the number of heads, and do that experiment, let's say 1,000 times, then if I add up my 1,000 observations and divide by 1,000, then we could look at that average. And the idea is the more, so 1,000 being the number of trials, the larger number of trials I use, we should expect that average to get very close to this. So this is really just kind of giving us an idea of what we expect to tend to happen in the long run.